The content in this presentation is covered on pages 146 through 151 of your textbook, and it's meant to help you achieve learning objective number 24, which is to write a statement relating the environmental lapse rate to stability. Be sure to skim those pages before watching this video, and also to read the chapter carefully before attempting the online quizzes. Why do clouds vary so much in size, and why does the resulting precipitation vary so widely? The answer to that question is closely tied to the stability of the air. Remember that when a parcel of air is forced to rise, its temperature will decrease because of expansion, and that process is known as adiabatic cooling. By comparing the parcel's temperature to that of the surrounding air, we can determine whether the condition is stable or not. Remembering that stability is the likelihood or lack of likelihood that that something will change. So if the parcel is cooler than the surrounding environment, it will be more dense, and if it's allowed to do so, it will sink to its original position. Air of that type is stable, and it resists vertical movement upward. If, however, the imaginary rising parcel is warmer, and hence less dense than the surrounding air, it will continue to rise until it reaches an altitude where its temperature equals that of its surroundings. This type of air is classified as unstable. Unstable air is like a hot air balloon. It will rise as long as the air in the balloon is sufficiently warmer and less dense than the surrounding air. The stability of the atmosphere is determined by regularly measuring the air temperature at various heights. This measure, called the environmental lapse rate, should not be confused with adiabatic temperature change. The environmental lapse rate is the rate of change in the actual temperature of the atmosphere with height, as determined from observations made by radiosondes and aircraft. Adiabatic temperature change, on the other hand, is the change in the temperature of an air parcel that it experiences as it moves vertically through the atmosphere. So in this figure, you can see how the stability of the atmosphere is determined, where the air at 1,000 meters above the surface is 5 degrees cooler than the air at the surface, and the air at 2,000 meters is 10 degrees cooler, and so forth. So the prevailing environmental lapse rate is 5 degrees C per 1,000 meters. The air at the surface appears to be less dense than the air at 1,000 meters because it's 5 degrees warmer. However, if the surface air were forced to rise 1,000 meters, it would expand and cool at the dry adiabatic rate of 10 degrees C per 1,000 meters. So when the air parcel reaches 1,000 meters, the temperature of the rising parcel would have dropped from 25 to 15. Because the rising air would be 5 degrees cooler than its environment, it would be more dense, and if allowed to, it would sink back to its original position. So we would say in that case that the air near the surface is potentially cooler than the air aloft, and therefore it won't rise unless it's forced to do so. The air just described is referred to as stable, and it resists vertical movement. So now we can look at three fundamental conditions of the atmosphere. They are the those three conditions are absolute stability, absolute instability, and conditional instability. When the atmosphere is under absolute stability, the environmental lapse rate is lower than the wet adiabatic lapse rate. And in those conditions, the air won't rise unless something makes it rise. Usually, if we do see clouds, they're very thin and cover wide areas. Any precipitation is likely to be light to moderate. And the best example of absolute stability is a warm front. And you can see in this case, there is wedging of warm air over cooler, denser air. So in a simple picture, this is what absolute stability looks like in the real world. To make things a little bit more complicated, this is the same process. We see an environmental lapse rate of 5 degrees per 1,000 meters. And that's up here in the top left corner of the figure. We see a wet rate that is slightly higher, 6 degrees C per 1,000 meters. And of course, we know the dry rate is always constant at 10 degrees C per 1,000 meters. If we state absolute stability in a quantitative way, this condition prevails when the environmental lapse rate is less than the wet adiabatic rate. So the figure we're seeing here depicts the situation using that environmental lapse rate of 5 degrees C and a wet rate of 6 degrees C. So notice that at 1,000 meters, the temperature of the rising parcel is 5 degrees cooler than its environment, which makes it denser. So even if this stable air were forced above the lifting condensation level, it would remain cooler and denser than its environment and would have a tendency to return to the surface. Despite that tendency to remain near the surface, stable air can be forced aloft, most commonly by frontal lifting, to some degree by orographic lifting. If stable air is forced above the condensation level, relatively thin, widespread clouds show up, and we see some light precipitation. Under absolute instability, this is the other end of the spectrum, we can expect to see in an unstable atmosphere big tall clouds starting to grow. So we see the convective uplift model happening here. And in this case, the environmental lapse rate is greater than the wet adiabatic lapse rate. So we see a lower atmosphere that's very hot, warm, right? And tall clouds make more intense rain showers. So like we expect to see the convective showers show up in the afternoons under these absolute instability situations. So this is, as shown in the figure, the ascending parcel of air is always warmer than its environment. So from the very ground surface to the top of the diagram here, at every point as this parcel is rising, its temperature is higher than the environmental rate, than the air around it. So absolute instability occurs most often during the warm months, summer months, and on clear days when solar heating is really intense. Under those conditions, the lowermost layer of the stratified atmosphere is much higher than the temperature aloft. And that makes a really steep environmental lapse rate. So you can see over here On the right, this purple line under the B part of the figure refers to this environmental lapse rate. So this is an environmental rate of 12 degrees per 1,000 meters, so much steeper than the one in the previous image. And you can see this is purple. But the parcel temperature is always to the right of the purple curve. So here the red line indicates the dry adiabatic rate, and that rate is higher, steeper than the environmental lapse rate, even though the ELR is very high. Then you can see a slower rate. That rate just lowers once we start adding that latent heat. So most of these situations, we see that steep lapse rate where the air temperature is rapidly decreasing with height. That makes a really unstable atmosphere. And convective lifting of the air near the surface makes towering clouds and the potential for strong thunderstorms. But those thunderstorms tend to dissipate after sunset because the main heat source here is the solar radiation. So those afternoon thunderstorms that dissipate during the evening hours, convective uplift in an absolutely unstable atmosphere. So halfway between those two conditions is a summertime phenomenon, the conditional instability. And that occurs when the moisture content is very high, so humid air. And the environmental lapse rate is between the two, the dry and the wet adiabatic lapse rate. So under those conditions, we see latent heat above the condensation level sufficient to make the air unstable. But that instability doesn't happen until you reach that condensation level. So we have to have the 100% saturation. We have to have a condition where the mixing ratio equals the saturation mixing ratio, and then we can see instability, and the cloud will grow up rapidly. That situation usually is associated with frontal lifting of really humid air, and so we see strong thunderstorms form. And so when the air has an environmental lapse rate between the dry and wet rates, we can see these big frontal storms occur. So simply stated, the atmosphere is conditionally unstable when it's stable with respect to the unsaturated parcel, but unstable with respect to the saturated parcel. And here's the diagram, by the way, that shows a very slightly higher environmental lapse rate than dry adiabatic rate. So you can just barely see the purple line to the right of the red line. Then when we reach that level of free convection, the condensation level is passed, right? We'll see the wet adiabatic rate greater than the environmental rate. So the word conditional is used because the air has to be forced upward before it reaches the level where it becomes unstable and can therefore rise on its own. And the altitude at which that air rises under its own buoyancy is this new term in here, the level of free convection. So use the content on the Canvas site and in the textbook and on the outside sources that are quality sources to verify that you can come up with answers to these questions. And if you can do that, then you're in great shape for the midterm. If you can't, reread the textbook, rewatch the video, and see if that helps your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.